For millennia, humanity has gazed at the stars, wondering if we're alone. We dream of finding another Earth, a twin planet orbiting a distant sun, a place teeming with possibilities. It's a fundamental question driving our exploration of the cosmos. But what if I told you the definition of Earth 2.0 is far trickier than we thought, and finding it might be closer, yet stranger, than we ever imagined? Not so long ago, the only planets we knew for sure were the ones right here in our celestial backyard: Mercury, Venus, Earth, Mars, and the gas giants beyond. The idea of planets orbiting other stars or exoplanets was mostly science fiction. Finding them seemed almost impossible, like spotting a firefly next to a searchlight from miles away. But human ingenuity finds a way. In 1992, the first confirmed exoplanets were discovered, albeit orbiting a pulsar, the dead remnant of a massive star, hardly Earth-like. Then, in 1995, astronomers Michel Mayor and Didier Queloz detected 51 Pegasi b, the first exoplanet found orbiting a Sun-like star. This discovery, which won them the Nobel Prize in Physics, opened the floodgates. Early methods, like the radial velocity technique used for 51 Pegasi b, looked for the tiny wobble a star makes as it's tugged by an orbiting planet's gravity. It was painstaking work, revealing mostly massive planets orbiting close to their stars, the hot Jupiters. These weren't Earth 2.0, but they proved planets were common. The universe, it turned out, was teeming with worlds far stranger and more numerous than we had dared to dream. This realization marked the dawn of the exoplanet revolution. So we know there are countless planets out there. But how many could actually support life as we know it? The first filter scientists apply is the concept of the habitable zone, often nicknamed the Goldilocks zone. It's that sweet spot around a star, not too hot, not too cold, but just right, where temperatures could allow liquid water to exist on a planet's surface. Liquid water is crucial, as it's the essential solvent for all life we know. If a planet is too close to its star, any water boils away. Too far, and it freezes solid. The habitable zone seems simple, right? But it's more complex than just distance. The size and temperature of the star itself define where this zone lies. Hotter, bigger stars have habitable zones farther out and wider than cooler, smaller dwarf stars. Furthermore, simply being in the zone isn't enough. A planet needs a substantial atmosphere to maintain surface pressure and trap enough heat to keep water liquid. Think about Mars. It's near the edge of our sun's habitable zone, but its thin atmosphere means liquid water can't persist on the surface today. Venus, though closer to the zone's inner edge, has a runaway greenhouse effect, making it hellishly hot. So the Goldilocks zone is a crucial starting point, a necessary condition, but it's not sufficient on its own to guarantee habitability. Enter the Kepler Space Telescope, launched in 2009. Its mission was revolutionary: stare continuously at a single patch of sky containing over 150,000 stars, looking for tiny, periodic dips in their brightness. These dips could indicate a planet passing or transiting in front of its star from our perspective. This transit method was incredibly effective. Kepler was a game-changer, transforming exoplanet science from discovering individual oddities to performing statistical surveys. It revealed that planets aren't rare exceptions, they are the norm. On average, there's at least one planet for every star in the galaxy. More importantly for our search, Kepler found thousands of planet candidates, many of them rocky worlds within their star's habitable zones. Planets like Kepler 186f, the first roughly Earth-sized planet found squarely in the habitable zone of another star, a red dwarf, or Kepler 452b, dubbed Earth's cousin, a slightly larger world orbiting a sun-like star in a year very similar to ours. While Kepler's primary mission ended, its data continues to yield discoveries, providing a treasure trove of potential Earth 2.0 candidates, and fundamentally reshaping our understanding of planetary systems. Kepler showed us that small, potentially rocky planets in habitable zones are common out there. While Kepler stared intensely at one small patch of sky, its successor, the Transiting Exoplanet Survey Satellite or TESS, launched in 2018, takes a different approach. TESS is scanning almost the entire sky sector by sector, focusing on the nearest and brightest stars. Why the change in strategy? Kepler found many distant planets, often orbiting faint stars, making them difficult to study further. TESS aims to find closer exoplanets orbiting bright stars. These are the prime targets for follow-up observations by more powerful telescopes, both on the ground and in space, like the James Webb Space Telescope. TESS uses the same transit method as Kepler, looking for those telltale dips in starlight. Because it's looking at nearby stars, the planets it finds are easier to characterize. We can more readily measure their mass using the radial velocity method, allowing us to determine their density and figure out if they're likely rocky, gaseous, or something in between. TESS has already identified thousands of planet candidates, adding significantly to our catalogue of nearby worlds, including potentially habitable ones. It acts as a crucial finder scope, pinpointing the most promising nearby targets for detailed atmospheric investigation, the next critical step in identifying a true Earth 2.0. Finding a planet of the right size in the right orbit is just the beginning. The real key to identifying an Earth twin lies in its atmosphere. Is there water vapor, oxygen, methane, carbon dioxide? These are the gases that could indicate not just habitability, but potentially life itself, biosignatures. This is where the James Webb Space Telescope, JWST, comes in, representing perhaps the biggest leap yet in our search. Webb is designed to study the universe in infrared light, which is perfect for peering through the cosmic dust that obscures visible light, and for analyzing the faint light filtering through exoplanet atmospheres. Using a technique called transmission spectroscopy, Webb observes starlight passing through a transiting planet's atmosphere. Different gas molecules absorb specific wavelengths of light, leaving unique fingerprints in the starlight spectrum. By analyzing these fingerprints, scientists can determine the atmospheric composition of these distant worlds. Webb has already delivered stunning results, detecting carbon dioxide and even sulfur dioxide, indicating active photochemistry in the atmospheres of gas giants. The ultimate goal is to apply this technique to smaller, rocky, potentially habitable worlds found by Kepler and TESS. Detecting water vapor, or tantalizing combinations like oxygen and methane together, in the atmosphere of an Earth-sized planet in the habitable zone would be a monumental discovery, bringing us closer than ever to finding Earth 2.0. So based on everything we've learned from Kepler, TESS, and ground-based observatories, do we have any standout candidates for Earth 2.0 right now? We certainly have some intriguing possibilities. Take the TRAPPIST-1 system, about 40 light-years away. It features 7 Earth-sized planets orbiting a tiny, cool red dwarf star. At least 3 of these planets orbit within the star's habitable zone. Because the star is so small, these planets are relatively easy targets for atmospheric study by Webb. However, red dwarfs are known for intense stellar flares, which could strip atmospheres and bathe planets in radiation, potentially hindering life. Then there's Proxima Centauri b, orbiting the closest star to our Sun, just over 4 light-years away. It's roughly Earth mass and orbits within Proxima Centauri's habitable zone. But again, it orbits a volatile red dwarf. Kepler 452b, orbiting a Sun-like star, remains a compelling candidate due to its similar orbital period and star type, though it's significantly larger than Earth, a super-Earth, and too distant for current atmospheric analysis. Other candidates like Kepler 1649c or Teegarden's star B also tantalize. It's crucial to remember though that potentially habitable based on size and orbit is a far cry from confirming an Earth twin. We're still gathering the data needed to truly assess these worlds. They represent the best starting points we have right now in this grand cosmic search. This brings us to a fundamental question. What do we actually mean by Earth 2.0? Is it just about finding a rocky planet, roughly Earth-sized, orbiting within the habitable zone of a Sun-like star? Or is the definition much stricter? Our own planet's habitability is a result of a complex interplay of factors developed over billions of years. We have liquid water oceans, yes, but also significant land masses. We have active plate tectonics, recycling chemicals, and regulating climate over geological timescales. We have a strong magnetic field, generated by our molten core, shielding us from harmful solar radiation. Our atmosphere has a specific composition: nitrogen, oxygen, trace gases, shaped in part by life itself. And, of course, Earth hosts abundant, diverse life. Would an Earth-sized planet in the habitable zone, but completely covered in a global ocean with no continents, count as Earth 2.0? What about one with a different atmospheric composition, perhaps suitable for life but not life as we know it? Does it need complex life, or would microbial life suffice? Defining Earth-like is surprisingly difficult. Perhaps we shouldn't be looking for an exact twin, but rather for planets that are simply habitable. Worlds capable of supporting liquid water, and potentially some form of life, even if it looks very different from our own home. The more we learn, the more we realize Earth might be quite special, and finding an exact replica could be exceptionally rare. The search is far from over. In fact, it's accelerating. While TESS continues its sky survey and Webb probes alien atmospheres, the next generation of planet-hunting missions is already in development. The European Space Agency's Plato mission, planned for launch later this decade, will focus on finding Earth-sized planets in habitable zones around Sun-like stars, specifically looking for long-period orbits like Earth's. It aims to characterize these planets thoroughly, measuring their sizes, masses, and ages. Another ESA mission, Ariel, will launch around the same time, dedicated solely to studying the atmospheres of a diverse range of known exoplanets, complementing Webb's capabilities. Looking further ahead, astronomers are dreaming big with concepts for enormous space telescopes designed for direct imaging. Missions like the Habitable Worlds Observatory, building on concepts like HabEx and LUVOIR, aim to directly photograph Earth-like planets around nearby stars, separating their faint light from the overwhelming glare of their parent star. This would allow us to not only analyze their atmospheres in unprecedented detail, but potentially even see surface features like oceans and continents. These future observatories represent our best hope for definitively answering whether Earth-like planets, and perhaps even life, exist beyond our solar system. The technological challenge is immense, but the potential payoff is arguably the greatest prize in scientific history. We stand at an extraordinary moment in human history. In just a few decades, we've gone from knowing only our solar system, to confirming thousands of diverse worlds orbiting distant stars. Missions like Kepler and TESS have shown us that planets similar in size to Earth, and located in potentially habitable zones, are common. Now, with the power of the James Webb Space Telescope, we are beginning to peek into the atmospheres of these worlds, searching for the chemical signs of water, and potentially even life. While candidates like the TRAPPIST-1 planets and Proxima b are tantalizing, the definition of Earth 2.0 remains complex, and confirming a true twin requires overcoming immense technological hurdles. Yet, with next-generation missions on the horizon, the prospect of finding habitable, perhaps even inhabited worlds, seems closer than ever. Are we on the verge of finding Earth 2.0? The data is pouring in, and the answer might just be waiting in the signals from across the cosmic ocean. Thank you for joining us on Tachyon Signals.